Okay, we're going to start with explain the meaning of the terms in the equation delta E equals Q plus W. All right, delta E is the energy. Q is heat, and W is work. So that equation just simply says the change of energy is equal to the heat and the work. It's applying to the energy. This is applying to the energy of a system. Whenever that energy changes, it's actually going to change by adjusting the heat or performing work. All right, Q, number 2, for a process is if Q for a process is a negative number, then the energy of the system is blank energy. All right, so energy of, if Q is negative, that means it's releasing heat. Therefore, the system is losing energy because it's actually going down. That's why it's releasing that energy. All right, next one is actually, it might need math. In this case, it really won't. I mean, I won't have to bring out a calculator. So it says if it takes 654 joules of energy to warm 5.51 grams of water, how much energy would it be required to warm 55.1 grams of water by the same amount? Well, all things being considered, I've just moved the decimal over. That's all I'd have to do on the energy. If it's 10 times the mass, it's going to take 10 times the energy. Okay, let's see. Need to scroll down. Next, number 4. We want to convert these units. In the first one, we're converting into from kilocalories to joules. Our conversion factor, we've got a couple we're going to use. First thing we're going to do is turn the kilocalories into calories. And then we have this wonderful definition that 1 calorie is actually 4.184 joules. Now, the next one, we're just going to be able to save our steps because we don't need to do that first one. We're just going to do that second one. 1 calorie is 4.184 joules. And next one, joules into kilocalories. We're basically going to undo what we did up there. So it's 1 calorie is 4.184 joules. And since I do want kilocalories, 1,000 calories is 1 kilocalorie. And last, I got kilojoules to calories. So we're going to convert our kilojoules into joules, and then convert joules into calories. And now I've written these down, bring up the calculator. So I have 75.2 times 1,000 times 4.1184. I get, that is 314,000 joules. Next one's not going to be nearly as big because we're just actually not putting the 1,000 in there. I don't need to do the math necessarily. This is just 314 joules. Our next one, 75.2 divided by 4.184 and also divided by 1,000, we get 0.180 kilocalories. And the last one, 75.2 times 1,000 and then divided by 4.184, we get 180,000 or 18,000. Okay, number 5. If 69.5 kilojoules of heat is applied to a 1,012 gram block of metal, and the temperature increases of the metal by 11.4 degrees, we want to calculate specific heat. Alright, so we have our basic equation. The heat is always a multiplication of the specific heat times the mass times the delta T, the change in temperature. The only thing I need to worry about is the units. So once my specific heat in joules, so I'm going to change my heat to joules as I write down the number. I'm just moving that decimal 3 places. And my delta T is 11.4. We're just going to solve for our C. So 69,500 divided by that, and then also divided by 11.4, we get a specific heat of 6.02. And be joules per gram degree Celsius. Did I type in everything right there? Yeah. Alright, number 6. If 125 joules of heat energy is applied to a block of silver, given a specific heat here, which weighed 29.3, by how many degrees would we expect the temperature to change? Alright, we're technically using the same equation up here, but now we're going to just do 125 joules. Give us the specific heat, it's 0.24 joules per gram degree Celsius. Give us the mass of 29.3, so we're going to solve for the change in temperature. 125 divided by 0.24 and also divided by 29.3, I get a change of temperature of 17.8 degrees. Technically that could be kelvins as well, because this is a delta T, and changes in temperature can be Celsius or Kelvin. Alright, what's next? Oh, that's right, can't scroll down like that. Alright, so number 7. It's actually got 3 parts to it. I think I'm going to make this so that fits the entire screen. Just those 3 questions. Alright, so for the reaction of sulfur reacting with oxygen to give SO2, we have a delta H of negative 296 kilojoules per mole. And our question is, we want to calculate the energy released when 1 gram of sulfur is burned in excess oxygen. Alright. 1 gram of sulfur, very first thing I'm going to do is turn that sulfur into moles. And 1 mole of sulfur is 32.06 grams. That's just the molecular weight of sulfur right off the periodic table. Now that I have moles, I can use this equation and that delta H as a conversion factor, because it says 296 kilojoules per mole. Now it does say SO2 form, but that's also the amount of sulfur that's being used up in that balanced equation. So that's all we have to do here. We just take our 1, divided it by 32.06 to get the moles, and then multiplied that by negative 296. And we get the answer of negative 9.23. And that'll be kilojoules. Alright, next one's a little bit easier because it's got the 0.501, but it actually says moles of actual sulfur. And we just do the exact same type of thing we did up here. 296 kilojoules for every mole of sulfur in this case. So 296 times 0.501, and we get 148 kilojoules. Now, next one's actually not going to involve any math at all, because it just wants to know how much energy is used to break up 1 mole. Well, that's how much is in that balanced equation, so it requires 296 kilojoules. Alright, last question, probably the toughest one on here because we are going to need to rebuild this equation using these three equations. I'm going to number these equations up here as 1, 2, and 3. What we're going to do is rebuild this by manipulating these equations. Because as you can see, most of our components are here, but we're kind of wrong on the oxygens, right? So we got to fix that. Alright, so what we're going to do is we're going to look for our very first reactant in our overall process. We find that in equation 3, and it has it exactly like it is. So we're just going to rewrite equation 3 here. Alright, now that takes care of that, but if you notice, I have O2 here, and I don't have it in my equation. So kind of what I want to do is somehow get rid of this O3 and leave some O2s behind, because I want O2s as the product. So what we're looking at is equation 1 is the one we're going to manipulate, but I'm going to reverse it right off the bat. Now, I'm not going to just leave it like that. I want to get rid of this O3. So along with reversing it, I'm going to change the coefficients. So I'm going to multiply all my coefficients by 1/2. I don't know why I did that. Reverse and half of it, equation 1. So that's going to be 3/2 of an O2 turning into just an O3 gas. And something I'm noticing here, I'm supposed to have a oxygen here. Just an O by itself as a gas. No subscript, no 2, no 3. Alright, now where I'm going to get that is I need to add that, and I'm going to get it from equation 2. But you see in equation 2 it has 2 O's, so I'm going to cut all those in half. So it's going to be half of an O2 turning into 1 raw oxygen. Alright, now I've created this, I want you to notice that the O3 as a reactant here and a product here, since they're on opposite sides, they cancel out. I have one whole O2 here. I have 3/2 and a half of an O2, so that would add up to 2 O's. So we're going to lose this, and this is going to go to just 1 O2. So what we're showing by pointing this out is that everything cancels, so we end up with an equation that looks exactly like the overall equation that we're supposed to have. Alright. Got to make sure that's not deleted on your worksheets too, because it might just be my program here. Alright, but now we have that. What we're going to do is take what we've done to these three equations and do that with the delta H's. So since we didn't do anything with 3, we're going to leave it like it is. Since we reversed equation 1 and we changed all the coefficients by half, we're going to multiply it by 1/2, and reverse it, we're going to change the sign of it. It was negative, now it's positive. And equation 2, we're just going to do by 1/2. Alright, so the first two become positive values, the last one becomes negative. So we have 427 times 0.5 plus 495 times 0.5, and then minus 199. And we get 262 kilojoules, which is what that equation works out to be.